Yeah, so continuing the talks that Britt mentioned, although it'll just be brief in this talk. I'm Gavin Brown. I'm a PhD student at Boston University. This is joint work with Marco Gabuardi, Adam Smith, who are also at BU, and with John Ullman and Lydia Zakanthinu, who are at Northeastern. Okay, so our task is Gaussian mean estimation in Mahalanobis distance. So given n IID samples from a d-dimensional Gaussian, where the mean and covariance are unknown, we'd like to output an estimate mu hat that is alpha close to the true mean in Mahalanobis distance. So we'll be using epsilon delta dp, and we don't put any assumptions on mu or sigma. So we're measuring accuracy in Mahalanobis distance, which is, I'm sure, familiar to many of you. It's kind of the natural error guarantee for general Gaussians. It's affine invariant. If the covariance is the identity, it's just the L2 norm. And it kind of informally captures the idea that we must have, our estimate must have small error in kind of the small directions of the underlying data distribution. So without privacy, you can do this task just using the empirical mean, which correctly gives us the error guarantees we'd like. And if n is roughly greater than d over alpha squared, then we get, with high probability, this Mahalanobis guarantee that we want. However, all prior private algorithms need either a d to the 3/2 samples for estimating the covariance, or required some strong prior information about the parameters of the problem. So our contribution is providing two algorithms that require no prior information on the parameters and need only roughly the empirical sample complexity. Both of our algorithms are exponential time, but just sample efficient. Okay, so in pretty much full formality, here is one of our estimators, which is based on the Tukey depth. Given n IID samples, if n is greater than d over alpha squared plus these two other terms, we hit our Mahalanobis guarantee with high probability. So this algorithm uses the exponential mechanism on Tukey depth with some kind of very basic and fundamental modifications that I won't be able to get into today. It hits the optimal sample complexity up to 1 log factor and requires no prior information, and actually matches the sample complexity for the known covariance. Even if I tell you the covariance exactly, this is the best you can do. We give an additional mechanism in the paper that is we call the empirically rescaled Gaussian mechanism that works for general sub-Gaussian data, needs slightly more samples by a factor of 1 over epsilon, and uses a fundamentally different approach. And so this is what I'll talk about today for the rest of this talk. Okay, but before we get into our approach, let's talk about using the standard Gaussian mechanism. So a folklore extension of the one-dimensional work of Carwin and Vidon. You take your data, you privately construct a bounding box and remove points outside of it. And then you calculate the empirical mean, and you release a noisy estimate where you add spherical Gaussian noise where C is set appropriately to ensure privacy. And if you work this out, if you want the Mahalanobis distance guarantee, the number of samples you need actually must scale with the condition number of the underlying matrix, the ratio between the max and min eigenvalues. This is a problem because condition numbers can be quite big in practice. The reason for this is basically that the Gaussian noise needs to scale with the size of the box, which needs to scale with the largest eigenvalue. And to get the error small enough, you need your, I have a picture here. To get the error small enough, the sphere needs to fit inside the smallest directions of your guarantee, the ellipse. So the spherical noise we're adding is basically ill-suited when the covariance is not spherical. Okay, so to our work, one thing we might like to do is add noise scale to the true covariance. We don't know this, so that doesn't work. The next idea is, well, maybe we can add noise scale to the empirical covariance. Okay, this would also be good for accuracy, but it's not private. Of course, adjacent data sets can have very different empirical covariances. So the next idea you might have is if adjacent data sets do have very different empirical covariances, then one must contain an outlier. And so we formalize this with a notion of good data sets which have no outliers. And we'll call a data set X good if for all data points I in the set, their Mahalanobis distance with respect to the empirical mean and empirical covariance of that set is at most roughly root D. This is satisfied by Gaussian data with high probability, sub-Gaussian data with high probability. So this definition gives us some subset of all data sets, which we'll just call G. And in our algorithm, we want to work only with data sets in this space. Okay, so what are we going to do? Given an input data set, we're first going to check if the input is close to this space of data sets, good data sets in Hamming distance. If so, we're going to somehow, exponential time, project into the set. If it's far away from G, more than like 1 over epsilon in Hamming distance, then we'll just fail. And if we don't fail, we'll release the empirical mean plus noise that's scaled to the empirical covariance, where we've calculated these empirical quantities after we've done the projection step. And we'll have to set C sufficiently large to ensure privacy. We'll talk about later. Okay, so let's talk about the accuracy analysis of this, which is actually not too hard. If the data is actually sub-Gaussian, our input data set lives in G. So the projection does nothing, and the noise we add is scaled to the empirical covariance of the underlying data. So as I claim, this is like the right noise to add. So I'll point out here, like, we are estimating the empirical covariance. We're getting a good estimate. We're just not privately estimating it. So recent work by Kamath, Mouzakis, and Singal shows that privately doing this estimation that we need requires d to the 3/2 samples. So we're not releasing this estimate, but we do use it in our algorithm. Okay, the privacy analysis is a little bit more involved. So I claim that the distance check is private. That's pretty easy because it's a set in Hamming distance. But what happens when we do this projection? So if I have an input x and an adjacent input x prime, when I project, I might actually increase the distances. My projection might cause these projected data sets to be even farther away than just one in Hamming distance. So what we do is we prove one of our central lemmas that says if two data sets, x and y, are both good data sets, and their Hamming distance is no more than roughly 1 over epsilon, which is exactly, okay, I don't know if this will work, exactly how far these two can be apart after projection because they weren't that far away to begin with, then the Gaussians induced by their empirical covariances are indistinguishable from each other. Which means that we'll be able to use this noise to still preserve privacy. We also need to show that the means are not too far from each other as well, which is, kind of uses a lot of the same ideas. And this is the core work in the privacy proof. Okay, so to elaborate on this, and let's look at why we lose on sample complexity in this particular algorithm. So I said our Tukey depth mechanism hits the optimal sample complexity, but our rescaled Gaussian mechanism requires d over alpha squared plus d over alpha epsilon squared. We get an extra factor of epsilon in there that we don't want. And this might be confusing because I told you we're adding the right noise. It seems like a pretty natural thing to do. So on input x prime after projection, I release this thing on the top. And on input x prime after projection, I release the thing on the bottom. And the idea is that I have to pay 1 over epsilon because the means are different, just like in the normal Gaussian mechanism. But in this case, I'm also releasing noise that has substantially different covariances. And so I need to pay an extra epsilon because these covariances themselves are different. So the noise is the right shape, but it's bigger than we think maybe in general is necessary, although it's necessary for this particular algorithm. All right, so in summary, we talked about the problem of Gaussian mean estimation in Mahalanobis distance and mentioned our Tukey depth mechanism, which I'll be glad to talk offline about, and how it works without prior knowledge of the parameters. We saw our empirically rescaled Gaussian mechanism, I'll mention that this idea of like releasing noise scaled to the empirical covariance without releasing the empirical covariance explicitly also shows up in other recent estimation work, by notably by Ashtiani and Liaw, and by Kothari, Monarangsi, and Belinker. As future directions, doing this in polynomial time seems like a worthwhile thing to do, I think. And also maybe improving the sample complexity of this algorithm. The projection might blow things up, but maybe you can get some kind of stable projection that sacrifices something somewhere, but ends up with nearby covariance matrices. So with that, I'd like to thank you, and I'm glad to take any questions.